Hello, my name is Nigel Browning, and today I'm going to be talking about accelerating EBSD through a mixture of sparse sampling and inpainting. So first off, let me show you what sparse sampling and inpainting is. You can see from these two images, we're actually only acquiring a very small amount of the pixels, and we're using a dictionary which is being learned from each of these images to actually reconstruct to get the full image to come out. Now, this is an iterative process. It involves learning the dictionary from this sparse sample data set and then iterating towards the fully inpainted image that comes up here. So as I go through and talk about the results for EBSD and other techniques in this presentation, this is the process that's going to be taking place. Now, let's just talk about the way that the dictionary learning works. And so here is a very simple example of dictionary learning that illustrates the type of process that we are actually doing as we do the experiments in a microscope. So on the right-hand side, we have a complex one-dimensional signal. And on the left-hand side, we have 4 dictionary elements, or Fourier components, if you like, that give rise to this signal. And each of these components multiplied by a scalar together gives rise to this final signal. Now, if we know what the full signal is, and we know what the dictionary elements are, or these components over here, then actually we don't need very much of that signal on the right-hand side to be able to fit these 4 dictionary elements to this signal. And only when you get down to a couple of percent, so 2 points in this case, do we start to see noticeable differences. So effectively, if we know what the dictionary elements are in any signal, image, whatever we're trying to look at, we can reproduce that signal very accurately from a set of components that come into that. And that's essentially what we're going to try and do with the compressed sensing. Now, the difference in terms of the experiment we're doing in a microscope is that because we're subsampling, we don't know what this signal is. And because we're subsampling and we're not putting any learned information into the reconstruction, we're only getting it from the image, then we don't know what these components are. But if we have the correct algorithm, and the one that we use is beta process factor analysis, or BPFA, actually it turns out that you don't need very much signal to be able to learn what these components are and reconstruct the whole process. And it can go down to about 1% of the data, which for an experiment in the microscope means that we can go 100 times faster and have 100 times less dose. Okay, now this can be moved up from working on one-dimensional images to look into 2D images. And here, rather than breaking up into these 1D components, or the image is broken up into patches. And each pixel is actually contained in multiple patches. And so each pixel essentially becomes one equation where you have the result, which is the pixel, and then multiple patches that are contributing to that, all multiplied by scalars to come through and cause the reconstruction. So this is what it would look like if we broke that image down to a dictionary. The full dictionary is actually very large, very complex. And this is actually the same way that JPEG reconstruction is done, is that actually what you want to do to make your image to be much smaller is that you can say that I'm going to approximate this patch here just by this one dictionary element multiplied by a scalar. Doesn't do a very good reconstruction, but if I shrink my image down to a very small amount, I can get away with it. But for our case, what we want to do is to say that actually we don't want the full dictionary because the full dictionary is very complex. What we want to do is to find the smallest number of dictionary elements that allow us to reconstruct our image without losing any information. And so this is the process that we're trying to do in our experiment. We're trying to take our number of pixels down as small as it will go. That will allow us to get the biggest dictionary that we can to be able to reconstruct our image. And we want that image to be reconstructed with no loss compared to the fully sampled image. And that's the process of the sensing and the reconstruction that comes out with the compressed sensing algorithms. Now, there's a reason why we want to do this other than the speed, and this is related to beam damage. Now, so if we're talking about beam damage in a scanned image where you have an electron probe, then effectively the damage must be initiated by the electron beam and it must spread out from the beam location. So if you're scanning your beam and you're going from one location to the next, what's going to be happening is essentially that process is going to cause you to create damage in one location and create damage in the next location. Now, if the beam damage goes very quickly or the scan is very slow, then there's a good chance that what will happen is the damage created at one pixel location will actually propagate to the next pixel location, and it will all cumulatively grow on top of each other. And if you've ever done a scanned image, you know that this can happen as you scan from left to right or top to bottom. Then you start to see a very high resolution image that begins to degrade because you either have contamination or beam damage taking place. And that's because the damage gets pushed ahead of the beam as the scanning takes place. Now, if we do sparse scanning and we jump around, then we're basically going to avoid this effect. Now, it's very easy to actually model this. You don't actually have to know very much about the damage. You don't have to know what it is, what the mechanism is. All you have to know that it's a diffusion process, which it kind of has to be when we're creating damage from the position of electron beam. And based on the time constant for that damage propagation, you can actually work out what the optimum probe is and what the optimum conditions are. And it turns out that it doesn't, that effectively when you're having a dose and a dose rate, those are not the only two important parameters that you need to have. You also need to know the order with which you're putting them into the sample, because depending on how you have that scanning pattern, the same dose and the same dose rate will give a different result in terms of the damage that will take place. Now, this has actually been seen very recently. This is an experiment done at Berkeley where they were doing 4D STEM experiments, and they called the damage impact craters. And they called them impact craters as a source of damage that extends beyond the beam position. And that's basically exactly the same as the overlaps that I've been talking about here. Now, of course, the way to get around this is if we add sparsity to our scan, so that what we're doing is jumping from one pixel to the next, but we jump over the impact crater to the next pixel location, then for the same beam damage, or so same beam dose and same beam dose rate, we get significantly lower damage in our result. And so effectively, we're talking about 5 times better signal to noise that we can get out of something because we're not dealing with the damage overlapping in a way that typically happens with a regular scan. Now, when it comes to doing sparse scanning, there are now many, many companies that will provide you with a scan unit where you can go through this. But the important point about this is that these are all hardware solutions. So they will do the sparse sampling. But the key to everything that I'm talking about today is really how quickly can you reconstruct your full image? Because getting a sparse sampled image is only the first part of it. You then have to implement the algorithm to be able to get the reconstruction to work. And of course, if you're going to do this properly and you really want to use it as a tool to help you doing advanced microscopy, then what you want to be able to do is to get that reconstruction fast enough that you can do it live on the microscope. And the best solution of all would be to not even notice that you're acquiring a sparse sampled image and getting it reconstructed. The reconstruction comes through fast enough that it just looks like it's a live image. And that is essentially the algorithm development that we've done at Sensei Vision. This is an algorithm that runs on a GPU. It plugs in through any one of the manufacturer's scan units that I mentioned a couple of slides ago. The one that's drawn here is by quantum detectors, or QD. This just plugs into the external port on any microscope, allows us to take over the scan, and allows us to do the reconstruction at speed, which means that we can increase the amount of speed for images in any scan mode by about a factor of 10 or more.
Sorry, I don't know.
Now, the first example I'm going to talk about is actually doing a 4D STEM. It's essentially the same method as doing EBSD, except you're looking at the diffraction pattern in transmission rather than in reflection. You get a full 2D diffraction pattern at every location of the beam. Now, there are several ways that we can sparsely scan this. One is by sparsely scanning the pixels. That's the bit I've talked about so far. The other one is sparsely scanning the detector. Each one of those will reduce the amount of time taken to form an image. But for today, I'm only going to talk about the scanning of the beam positions and reducing those. So here's an experimental result. This is a sparsely scanned image taken from a Joule 300 kV grand arm at the Rosalind Franklin Institute. These are the diffraction patterns that are acquired at every one of these pixels. It's about a 25% scan, so only 25% of the pixels are being acquired, and you're getting a live reconstruction of the atomic resolution of these gold nanoparticles coming in here. Now, because this is not a AI method that requires training data to go into it, it's all solved from the image. You can change magnification, you can change focus, and your image will change in real time, and you can reconstruct it. The other thing about this is that we're not using training data, which means we don't have to worry about hallucinations. So typically you can get hallucinations with AI. What happens with compressed sensing is what you can see down here in the bottom left corner of this image. Effectively, there's not enough information in the sparse scanned image to get an atomic resolution result down here, so it just shows it as an unresolved piece of the particle. And that's essentially what happens when we do sparse sampling. You get a very accurate reconstruction. If it can't reconstruct the data at high resolution, it just shows you at the resolution that it can get. So this is the process to get the sparsely sampled images. Now, in those images that I've just showed, our goal there was to get the images to reconstruct as quickly as possible. And those images there were coming in about 10 frames per second. It was slowed down in the way it was being presented because the computer was running the reconstruction and the whole thing together, but effectively it was being acquired at 10 frames per second. Now, after we've acquired the image and we've got that complete data set that we've taken from the gold nanoparticles, we don't need to be quite as fast anymore. So overnight, after you've acquired them, you can then run the whole thing through, except this time, rather than trying to get speed, what we're going to try and do is to get the best high spatial resolution image. And using exactly the same dictionary as we had when we're running the live reconstruction, we can actually increase the spatial resolution of our reconstruction. This is not increasing the spatial resolution of the image. It's all here. It's a lower signal to noise, but effectively that resolution is present. So here you can see the gold nanoparticles has much higher resolution, including that bit where we couldn't quite resolve it in the live image. We can also see individual atoms in between these larger gold nanoparticles. These individual atoms are essentially seen moving around, and you can see those very, very clearly. So we also can deblur, denoise, and get very high resolution. Here's another example in transmission. For now, this is nanobeam electron diffraction done with nanomegas. Using the nanomega system, here is the phase map that comes out of this. Here is the reconstruction. Again, 25% of the data being acquired, and the full reconstruction gives you pretty much the same data that you can see very clearly. Not only that, when you do the distribution of the profile of the grains and the areas, you get pretty much the same histogram. There's a little bit more noise in the 100% one, but effectively you've got the same distribution that's coming out of it. So getting 4 times faster without any problem at all in terms of signal to noise and recovering all the data. All right, so let's talk about how this would work for EBSD. EBSD, we're using an SEM very similar to the STEM approach, scanning the beam of the specimen, except we're going to collect the backscattered diffraction patterns. So at each location of the beam, we're going to collect one of these patterns, and then we're going to process these patterns to convert it into an image, whether that's a pole figure or whether that's a band contrast map. We're going to convert it to form our image. Now, in our process, we can either inpaint each of the individual each of the individual diffraction patterns, or the whole map. Okay, so this is the process for EBSD. Now, the two processes we call post-index and pre-indexing. Post-indexing, what we're going to do is we're going to miss out some of these diffraction patterns, but we're going to convert the information that we have into our map. And the example here is a band contrast map. So once you've got that subsampled band contrast map, as far as the algorithm is concerned, it doesn't know anything about this other than it's an image, and so it's going to inpaint the image. The second approach is which we call pre-indexing, which is to say, we've got these missing diffraction patterns, so what we're going to do is we're going to inpaint the missing diffraction patterns and create diffraction patterns in places where no data has existed before. Once we've got that full data set, we're going to then take the full data set and create the band contrast map or whatever we want to convert over it. So there are two sides of it. One is inpainting something which is related to the physics of scattering, and the other one is just inpainting the image. And each one will involve a trade-off in speed and accuracy, which I'll talk about as we go through this. Okay, so the first case, we're going to do artificial subsampling. Now, what we mean by artificial subsampling is that we're going to take 100% sampled image, which is our ground truth, and we're just going to start throwing away data randomly to see how much we can throw away and still reconstruct and get our ground truth data back. So here's the process that we're going to do. It's a data nickel superalloy, Oxford Instruments system on a Zeiss microscope, typical dwell times, but now we're only going to go with 25% of the data. All right, so first thing, post-indexing. So again, to be clear in the process that we're going through here, the algorithm simply sees the image at this point. So this image is created by the Oxford Instruments software. We're not, in doing the sparse sampling, changing anything about the physics of the process on the detector. And we're not changing anything that goes into the Oxford Instruments software for the reconstruction and the forming of the maps. All we're doing is saying when that map comes out, if it doesn't have all the data in it, we are going to inpaint the missing data. And as it's an image, it doesn't matter where that data comes from, it's just painting the image. All right, so here's an example, simple example to start with. Here is just assuming that we've got 77% of the data, so it's not throwing away very much, it's not speeding up very much, but you can see that you've got all the information in the subsample map, and then we get the information coming out when we do the reconstruction. Okay, so we can fill in the missing pixels, we know where they are, we can inpaint them, and we can get the reconstruction coming out. Now, let's go to something a little bit more challenging. So this is actually where we've only got 4% of the data. And you can see in the patterns that are coming out, you can sort of identify where the grains are, you can sort of identify where the grain boundaries are, but this is clearly not a very high quality reconstruction that's coming out. When we do the reconstruction, you can get a much clearer picture. You can find all the grains, all of the orientation effects are being identified very clearly in this. You can see it looks a bit blurry. And the blurriness is what I should have said before. Because we're going for a very quick reconstruction, we're getting something where we're filling in the low spatial frequencies. We haven't done the filling in for this one specifically, but I'll show one in a minute where we've done the deblurring, and you can effectively get through and reconstruct the image. So here it is after the deblurring, going through that process. You can effectively get a very, very high quality reconstruction with only a very small amount of data that you're actually acquiring. Again, not changing the physics, not changing the detector, just basically using the missing data and filling it in. Now, the important point of this is that it doesn't matter what your detector is. So if your detector needs a dwell time of 1 microsecond, then we can speed it up by a factor of 10 on that. If your dwell time is 1 millisecond, you can speed it up by a factor of 10. It doesn't matter what the camera speed is. If the camera speed can get enough signal to noise to get you the reconstruction, then you can speed it up by the factor of 10 when you do compressed sensing. So it makes not very good detectors better, and it makes very good detectors even better. And here's an example of the band contrast map. Again, you can see slightly blurry, but you actually get the reconstruction to come through, and you get the image as expected. All right, so now let's go to the pre-indexing. What we're doing in the pre-indexing is essentially knowing what we do about the data set and the structure that comes out. We can inpaint the missing patterns for the pixels where we didn't acquire them to get our full data set. Once we've got the full data set, then the normal OI software to do the reconstruction is used. And so it's not changing the physics of the process. It's not changing the way the index is being done. It uses the software that already exists. All it is doing is inpainting the missing EBSD patterns. Now, the thing about inpainting the EBSD patterns that are missing are because essentially each inpainted pattern can use all the signal to noise of all of the images that have been acquired, or all the diffraction patterns that have been acquired, then you actually get an increase in the signal to noise from the inpainted patterns that didn't exist. And so this means that they're less noisy, they're better references, and they allow us to identify the maps with higher precision. Now, we know where the problems are going to lie, and this is just talking about the data set and the signal to noise you get into it. Effectively, what happens is always we know that the grain boundaries and interfaces will have a lower signal to noise. So we're going to have to deal with that. But the key part about this figure is just to say that when we're inpainting the information, it still fits on the same distribution. So it's not like the inpainted data sits at a smaller PSNR or at a higher PSNR. It all fits in with existing data sets. So we're not creating something out of nothing here. We're creating EBSD patterns that are related to the data sets we've got and is filling in the missing information in a pixel by pixel basis. Now, when you go through this process, you actually can get a very, very high quality data set that comes out. And it's greatly improved the clarity of the grain boundaries. You can see it's not blurred in any way. In fact, the precision and the sharpness is increased over the 100% sampled. Now, the reason for this is, of course, that we've got higher quality information that we're inpainting in the diffraction patterns. That higher quality information is going into the OI software to create these band contrast maps, and so that effectively is going to give us a better image that's coming out. Same thing for the pole figures. If we go through that process, we're putting better information in, we're getting better information out, and the map is going to have higher quality, even for very low sparsity. The trade-off is, of course, that to inpaint a 2D diffraction pattern at every pixel location is a much higher computational effort than just inpainting an image. And so inpainting the full data set in the pre-indexing is a little bit longer. It's not something that we can do live, but what we can do is after we've finished with our live imaging, we've set it up using our post-indexing, we can then do a reconstruction with the pre-indexing, and we can get a much higher quality at the end of the day. And here is just a comparison of that. And so you can see the process. Now, the interesting thing about this is that in this case, for the band contrast, the SEM and the PSNR seems like it's gone down when we've gone to the pre-indexing, even though I said it was a better reconstruction. And you can see that it is a better reconstruction. The thing is that this has gone down because these numbers are compared to the reference image. And if the actual map is increased better than what you had in the original case, then the similarity and the PSNR is going to go down. This one in the middle is closer to the original. This one is better than the original, and so the numbers are going down. Okay, so we can get the high quality we can get out of that, and these results are following the trends that we've got from every single reconstruction we've ever done with sparse sampling, and it says that as long as we keep above 10%, we'll get a lossless reconstruction, very high quality. Now, that's not to say that you can't go below 10%. I showed a result for 4%. The problem is that you just have to be a little bit more careful in the reconstruction, and you might lose a little bit of information in getting to that point. But you don't always have to have the same resolution as you have with 100% sampling. If you have beam damage, if you have charging, if you have contamination, there are all kinds of problems, then it's better to do it that way and to get a lower sparsity and lose something in the reconstruction than have nothing at all. All right, now people don't typically use EBSD on its own, use other methods. Here is just a quick demonstration of using EDS analysis. In this case, we're looking at quartzite, which is 10% feldspar, 90% quartz, and the feldspar has aluminum in it. So we're going to use the aluminium K-edge to just basically allow us to go through and map out the structure. So 400 microseconds, the gold standard in terms of what you'll do. You can see there is an interface length, there is a phase area, and there is a compositional map of aluminium. Now, as we go down to faster and faster acquisition time, as expected, the compositional map gets less clear, the amount of aluminium we find is much less, and identifying the phases and mapping out the boundaries becomes a lot harder to do. Nothing surprising with that. We know that's the case. We lose accuracy when we go to shorter and shorter acquisition times. But if we now use BPFA to denoise the system, we can go to shorter and shorter acquisition times. We still get the accuracy in our composition analysis down to 20 microseconds. This is still within the error bars, no problem. We still get the length of our interface correct. We still get the area of our phase correct. And you can get much, much lower signals and get much, much higher resolution out of it using this to do the denoising. Now, if we add inpainting to it, we can even go a step further. we can get, you don't even need the 400 microseconds, you go down to 65 microseconds, and you get very high quality results in terms of the composition and in terms of the phase area and the areas of the grain boundaries. And so essentially we get the same accuracy, but we're now 50 times faster in our EDS maps. So we were talking about EBSD being 25, 30 times faster, EDS maps 50 times faster. And the key thing is you can perform both of them at the same time. There's no reason to do them separately. You don't have to have a change of conditions. We know that we're going to have not quite the optimum to do both at the same time, but it doesn't really matter because we're going to help each one to do the reconstruction. And just an example of that, we also know that when we run an SEM and we're doing this kind of mapping, we can also do things like backscattered electron images. Now, backscattered images have the highest scattering cross-section. So if you get a BSE image, it has very, very high quality. This is a different alloy, but it's still looking at the aluminium edge. And if we blow up the magnification of this area here, it looks like we have a sparsely sampled result in this case. But this is just because the signal to noise isn't enough for us to be able to measure anything. But this is sparsely sampled, so we should be able to inpaint it. This is a very high quality image that's acquired in exactly the same way as this one. So each pixel in this image corresponds to a pixel in this image, which means we could take a dictionary from this image and use it to reconstruct this one. And here's an example where that's being done. Again, same alloy, looking at the aluminium edge, low signal to noise, sort of can see the shapes going on here. But if we use the dictionary we got from the backscattered image, we can get a very, very high quality reconstruction of the aluminium in the structure, so we can identify the phases. And the image itself has a mixture of the surface sensitivity of the backscattered electron image and also the compositional mapping of the aluminium signal. So I hope I've shown you that we can do a lot of things with compressed sensing, speed up, EBSD, EDS, backscattered imaging, pretty much any scanned image that you want to do. These are the people that have been involved in this, the people at SenseAI, the people at the University of Liverpool, and many collaborators around the world. Now, I want to finish up by talking about the IMC meeting, the International Microscopy Congress. This year is going to be in Liverpool, August 30th to 4th. The deadline for abstracts has now passed, so you can't submit an abstract. But the deadline for late-breaking posters is still open until June. So please submit any abstract, submit your poster, and come and visit Liverpool. Come and see the home of the Beatles, the home of one of the world's great soccer teams, and also see why Liverpool was once the richest city in the world. There's lots of engineering going on there, lots of things to see and do. And it's a European city, so everything is in walking distance of the docks here. All right, and then finally, all of this is really being commercialized by SenseAI Vision. At the moment, we're looking for beta testers. We have a very old version of the code you can download if you want to try that, but it runs so slowly, I don't think it's really worth doing anymore. But we are looking for beta testers to do the installation. The installation of our software is plug and play right now. It takes about 2 hours to set up on any microscope to convert any microscope into a sparse sampled imaging system. So if you're interested in that, please go to the website, send me an email, contact me in any way you want, and we can sort something out like that. And with that, thank you very much for your attention. Obviously, I'm not there, so I can't take any questions. So please just write any questions down, send them to me, and I'll be happy to answer them. Thank you very much.